right, good morning. Guys have a nice weekend. A couple of you very nice. Nice long weekend. So hopefully everything's good on that front, and maybe you enjoyed. Maybe I should have given you some homework to appreciate Labor Day properly, right? I gave myself some because I knew I don't love preparing the lecture until I'm like about to teach it, and I don't love doing it first thing in the morning. So I saved that for yesterday to do. So I was celebrating Labor Day with a little bit of work. But happy to hear some of you had some more exciting things to celebrate. Okay, last time we left off here with the kind of just fundamentals of concentrations, digging in. So we're going to pick up here in a moment and continue and really lead into thermodynamics and lead into where we had already introduced a bit of like the equilibrium kind of basics. The book just hadn't got there yet, so I touched on it, and we're going to develop that a little further today and get into the difference between modeling a system by kinetics, meaning how fast are things going one way or the other, heading towards equilibrium, versus assuming we're already there, and what do we do with that? Now, I meant to take a little more time looking through the feedback you gave me. Thank you for that. I will spend a little more time making sure I read everything. But I took a glance just now, and I was surprised to see that a lot of you are interested in learning programming, MATLAB, something like that. So I'm glad you're not all scared and like, no, please anything but that. Having said that, I had one formal course on MATLAB and then a couple different courses throughout my college and grad school using it. And then I've played with it for a few little projects here and there afterwards, sometimes academic, sometimes not, just sort of for fun, but it's been a while. So I've never taught it, so I will start incorporating a bit. I'll make sure I can get it on my laptop here so we can play with it here. And I'll also give you guys a little bit of basic homework in terms of, okay, figure out, can you get it on a laptop and bring it to class? Is that feasible? Can you remote desktop into a computer lab computer? What can you do so that I can know how can we approach it in class? So I'll start adding in small pieces. Okay, write a script that returns hello, or that calculates 2 plus 2. You know, something basic, and see. You know, so I'll make sure to start that pretty early as we go through the chemistry, so we can start working towards both together. Worst case scenario, we don't get very far with the actual MATLAB instruction, but far enough so that we can load up and understand how a system is working that somebody else has developed. So we might not be writing the code ourselves to solve an equilibrium problem, but I know that there are public sourced pieces of code that we could do just that available online. So we'll do something to that effect, if nothing else. Okay, and today we'll also mention the EPA has a system called MinTech that's out there. I think when Dr. Pardue teaches this class, I was looking at his syllabus, he goes through that, and so I might also try to take a look into that. I just have never touched that myself, so I was starting with what I know, which is MATLAB, but the MinTech is certainly a popular tool for this, so I'll make sure that we have at least some discussion on that and learn more about it myself. Okay, so any questions or issues, thoughts? All right. So we were talking about concentrations. We were talking about how are we approaching molarity versus molality, why we might care, how do we describe a particular solute in a volume of water or in a volume of solids even, and how do we deal with that? So that's kind of where we were. Got a table here describing some of the basics, kind of summary stuff. You all kind of know this already. But we can describe, if we're talking about milligrams per liter, well, if we put that into weight fraction, that would be milligrams per 1 kilogram. Now, you'll notice that at 5 degrees Celsius, 1 kilogram of water is 1 liter. So that's why it's approximately equal to, at room temperature, it's not exactly, but it's pretty close. So that's why for a aqueous solution that's not too saline, 1 milligram per liter is approximately 1 milligram in a kilogram, and we can then also describe that as 1 part per million, because we have 1 million parts of water per 1 part of that solute. So, and just as a quick reminder, I think I already mentioned this, but I blur it with the other class. So 1 ppm is the same thing as saying 1%, except it's not percent, it's per million, right? It's not per 100, it's per 1 million. So we could say that's 1%, but then we just have to add a bunch of zeros, kind of thing. Okay, so of course we can use micrograms and nanograms. Same conventions here, we just change the order. So 1 microgram per liter, that would be 1 microgram per kilogram, and so on. So that would be 1 parts per billion. 1 nanogram would be 1 part per trillion. We don't typically go too much further below that. Occasionally in certain systems, picograms, so that's 10 to the minus 12 is pico. And then if you're going any lower than that, you're probably using some other dimension. Of course, you could, if we had the tools to describe that or to detect that, we could go to femto, but typically that's more like if you're using lasers and doing really, really fast pulses, or the time dimension is when you'll more often see femto stuff. So it's not really relevant to concentrations, but typically we don't really have analytical capacity to go below nanograms. That's pretty rare even in and of itself. Okay, so we need to talk about activity, and I think maybe we almost got there, or maybe we mentioned it, but concentration is convenient to work with because we know that, okay, this is the amount that's in solution. Activity is in a way more important because even if we have 10 grams of some solute in a liter of water, it does not necessarily act like there's 10 grams of it. So the activity of that reactant is really important. So you could have a situation where you have a chemical and just its neighboring solution stops it from activating, stops it from reacting quite so fast. This is sometimes why you might have to heat something up or attend to the other conditions. Maybe there's some interference if you are doing some chemical reaction. Activation energy is separate, but that would also require heat. Okay, so activity then, it's as if you're potentially slowing something down. We would describe that as the activity of I and give it the squiggly brackets. Anybody know the formal name for those? To me, this is a bracket and that's a squiggly bracket, but I think maybe there's a better term. Okay, so we're gonna write it as the squiggly bracket, and we can say then we could also write it as the activity of species I. So I could be any solute, right? So the activity of that solute is equal to the concentration, the molar concentration with the regular brackets, times this gamma I, which is our activity coefficient. So we're going to spend some time describing these and kind of why this comes about. When we're doing chemistry, and especially as we get to thermodynamics, we often want to end up using or being careful with our dimensions, our units. And so as we think about this gamma, it has to be dimensionless, because when we are trying to describe the activity of something, it's as if we're saying the effective concentration of it. So this guy is the effective concentration in terms of how it's going to act. So if our gamma is 0.5 and we have 1 mole per liter of this stuff, then it's that 1 mole per liter is going to act like there's half a mole per liter. So then when we have some reaction that's happening, the system will act like there's half a mole per liter of that something. So if we have a time-dependent situation or something of that nature, we can expect that the dynamics of the system will act accordingly. Okay. Now, the I here, I think I mentioned molar, so moles per liter, but it's actually the molal, so moles per kilogram. Scale in a dilute system, that's pretty much moles per liter. But this will be important occasionally. So this will say moles per kilogram here. So this is all to say that's the activity of I in that system. Okay. And it describes that dilution, right? So typically the molality versus molarity, we already talked about that. In dilute water, it's essentially on the molar scale. Now, we can never have an activity of 0. It can be pretty close to 0, as if like it's almost non-existent, but it's never going to go fully to 0, and we can't have a negative number there. So because a negative concentration physically does not make any sense. So we'll say the activity of some species, let me draw a better gamma here, is always going to be less than, or so greater than 0. Technically, you can have above 1. So in particular conditions, maybe you have a system where the species is acting more active than you would have expected. That is theoretically possible, but it's never going to be 0 or less than that. Okay. Now, when we then go to put this in kind of thermodynamic terms, we're often going to look for that unitless condition. And so we can take this a step further and say, well, this activity, we can describe it as, and this is a way to get rid of the units altogether for ourselves. We can take the concentration, the mole concentration of I, and divide it by sort of a standard state or a reference state. So this is the I with the degree symbol here. I'm not quite sure how we describe that, but you've seen this before, and I'm sure we will see it again soon with the Gibbs free energy kind of stuff. So that's a reference state of some sort. And this guy is going to have a magnitude of 1. So this guy is 1 with the same dimensions of I, and that will give us a dimensionless situation. So what we're describing here is that by putting that, dividing something by 1, it kind of does nothing, right? So it's, as I showed over here, when we divide by 1, it's kind of the same thing as just having that there. But we can make that statement where we're saying that this I at a standard state plays a special role in this thermodynamically as it refers to a hypothetical standard state. So that standard state being its activity if all things were completely standard. That's why it just becomes unity there. So that's actually going to explain for us in a minute why in our equilibrium thing with water, we treat liquid water as 1. It's very related to this concept here. But okay, so let me come back to this. So this is just an elaboration, but what it does is it lets us get rid of our units here to have a dimensionless number for when we need to do a logarithm in thermodynamics. Okay, so for aqueous solutions, in the mole scale, this gamma are defined to be unity in very dilute solutions when the concentration of with the concentration of I. So if we have I in solution and it's dilute enough that it's just going to interact with anything around it as if there's nothing disturbing it, it's just the water around it, that's the standard state. So its activity then is at unity. So that's our description of it, and that can give us a way to work with two unitless numbers here, and keeping this unitless and keeping the whole expression unitless. Okay, so looking forward, when we're describing the units, they can affect the equilibrium values, K, but the units are never going to actually change the underlying thermodynamics. So, for example, when we were talking about water, and we said water is going to be in equilibrium with H plus and OH minus, and we had some equilibrium constant, Kw, we derived and described that Kw, that was the 1.01 times 10 to the minus 14. Now, we can leave that dimensionless, but that means, so the way we described this, and we'll see as we develop this, we said that's going to be equal to the products over the reactants. Liquid water on the bottom. So if that's unitless, then it's kind of strange, because if Kw is unitless, that means the units of mole per liter times mole per liter, or moles per kilogram times moles per kilogram divided by this guy somehow has to become unitless. So it's a little bit of a strange circumstance. But we can say the strictest way to say it would be Kw has a value of that dimensionless at 25 Celsius and 1 to atm, 1 atmosphere, when molality is the concentration scale chosen for both H plus and OH minus, and mole fraction is the concentration chosen for water. So if we take molality and we apply what we were just talking about, we can get that. I think that's what it's describing, is we can get both of these on top as unitless in that sense, and we need the water as a mole fraction. So mole fraction of water, so much of the water is just water, barely any of it's the OH minus and the H plus. It's pretty much 1. Okay, so if we describe it as a mole fraction on the bottom, that's where the 1 makes sense. So when we describe all of this together, that's a lot to say. So typically we just kind of say, all right, well, we're just going to leave unsaid the fact that we're doing funny things with the units, and we're going to leave it as kind of moles per kilogram squared, or in water, moles per liter squared, basically. And just deal with it. That's the long and the short of it, okay? So it's just elaborating on all this stuff. We see that there's a reason for it. We could be very strict about it, and even the author is like, yeah, let's not be quite so crazy about this. Maybe it's nice to be so exact with everything, but don't really have to. We can shorthand some of that. Okay, so that kind of explains where we get the 1 for the pure liquid water, and that kind of makes a little more sense. And yeah, we've got funny units going on with equilibriums, but that's okay. We'll just leave it at that. Okay, so molal versus molar. When we have a reference state, this is just an elaboration on kind of what I already mentioned. When our reference state is kind of what dictates that when we're looking at I here, right? So the reference state for a solute is when we have an infinite dilution. So this is, I'll just draw this. So when we have infinite dilution and one molecule of something dissolved in water, all it sees is water. Here's our reference state, okay? When we have pure water, all we have is water. And so everything around it is water. And therefore, our reference state, that's where we get kind of the suggestion that liquid water goes to just one. Okay, and that's the mole fraction. Moles. This is moles water per moles water, or solution total, right? Okay. All right. So then another little piece here is we can use this this guy, just kind of denoting the same thing. If we ever needed to express it in a solid instead of a liquid, all of this kind of still holds true. We can describe activity in the gas phase also. It's pretty similar. We're not going to deal too much with gas phase stuff, a bit of it, so we might come back and look at this a little bit. But then we have a system where the pressure can change and the volume may also be important. So there are some things that would then, if we have a few gas molecules in a very, very large volume, it's kind of like a vacuum, they're very unlikely to interact with each other. Now we take that, put more gas and shrink the volume, the activity is going to change because they're bumping into each other so much more, right? So things like that, we can get a sense for that we will have a change. Water is almost incompressible, so it's harder to have that sort of a change. And you'd have, of course we can look at that in water, but typically for most aqueous chemistry, our volume is thankfully pretty constant. Okay, when we deal with gas, we can recall that there's the ideal gas law. Pressure times volume is equal to the number of moles times a constant times the temperature. Now, the units we use there, will determine what units the R is in, but we have those relationships and we can use all that. All right, so kind of mentioned this to an extent, but we can summarize. When we have this gamma value for the activity coefficient, if it's less than 1, we have more of the stuff in the solution than it seems like we do if we were to look at the reaction, right? The reaction is just simply happening slower. If our gamma is greater than 1, then we're getting more reaction than we would have expected, or more interactions. Of course, when it's equal to 1, that's pretty much ideal behavior. That's what we would like to have in many cases, just to simplify things. And this is often what we've always assumed in general chemistry or other chemistry classes, right? So we probably mention activity sometimes, but for most of the time, this is, we'll say, often assumed, at least in class. So it might be worth thinking about if we have different situations. It actually reminds me of the chemical method that Maddie's been working with me to develop, makes me think, I wonder if we're running into some activity things here that might be explaining why sometimes our concentrations are slow to get to where we thought they should be, or something strange is happening. Just don't quite know the chemistry enough, and maybe that's part of this is an activity issue. Okay, so sometimes it can be relevant. But ultimately, we have a way to calculate for that and figure out what's going on. Okay, and again, technically these are molal scales, but in dilute solutions we can use molar. Okay, so what drives activity is kind of the next logical question, or maybe something that we could have asked beforehand. And I mentioned this, but it's really the action, whether it's hindrance or acceleration, that's occurring based on neighboring molecules. There are likely other factors as well, but it's really going to depend on the matrix. You know, if we were to play some sort of game in this room, maybe tag, and start running around, the desks are going to interfere a lot over there. Over here, not so much. So the activity of somebody running around over here would be less limited than over there, right? And so you'd be climbing over desks and things and bumping into each other or objects a lot more, and it'd probably be painful to play tag over there compared to over here, right? So we can see that's the type of dynamic that might be happening in solution with a complex matrix. Okay, so let's think for a moment about magnesium chloride. When we dissolve magnesium chloride solid, it's going to dissociate into Mg2+ and 2Cl-. So that means for every one magnesium chloride, now we have a 2+ here, Cl- and another Cl- hanging out in solution. Of course, there's water molecules and OH- and H+ hanging around too. So we can imagine that the 2+ is going to pull negative charges differently than the Cl- is going to pull positive charges, just by the nature that one is more densely charged and the other just has a single charge and is hanging out there. So what happens? Well, if we take a look at an example of a 0.01 formula weight solution, so that's just meaning moles per liter of this stuff. So we dissolve 0.01 moles of magnesium chloride in a liter of water. Well, the Mg2+, it turns out that the activity coefficient is about half, so 0.51. Whereas the Cl- is closer to normal, closer to the standard, which is at 0.85. Now, if we up the concentration by an order of magnitude, so 0.1 moles of magnesium chloride per liter, then we check again, magnesium chloride is down, or so, excuse me, the magnesium is down to 0.25, and the Cl- dropped to 0.71. So this impact, the activity showing for the two different species, it's having a more profound effect on magnesium, given that 2+ charge, than the chloride. So the chloride is still staying fairly normal in terms of how active it is in solution. Another way to look at this, we can describe kind of a second example here, and then think about it in the context of magnesium chloride. The acid dissociation for a simple acid looks like this. We have a proton, the H, attached to an acid, could be something like HCl, right? And it's in equilibrium with H+, and its corresponding conjugate. So in my example, Cl-. So in an acid like that, we're going to give off that one proton, and if we have 10 to the -5 formula weight, so 10 to the -5 moles per liter of that acid, and 0.005 moles per liter of NaCl, then what happens is we end up getting the H+ surrounded by Cl- and the A- surrounded by Na+. So these charges are going to be interacting. So in this case, we've gone a step further and said, well, not just water, what happens if we have sodium chloride and an acid? Well, this is kind of what's going on. We have these ions are surrounding the other species and interacting in this sense. So suddenly, if you replace these Na, like if you replace two of these with one Mg2+, you'll notice that there's not so many, that's going to change the dynamics, right? It's going to be less opportunity for the magnesium to interact with acids. If you have the same number of magnesiums, you're trying to, they're trying to find negative charges, right? And so the extent to which they're able to is lesser, and they're having a stronger pull for those negative charges because of the density. So we can see then that's the type of competition, that's the type of dynamics, that pushing and pulling, that are going to be changed if we have a lot more of a salt compared to the acid around. Of course, there's also going to be some interactions between, you know, the charged species here as well, but all of this is to show the types of dynamics. So this is the table that was kind of describing this stuff a moment ago. And if we take a look at what it's saying about this figure, it's just kind of a schematic of the ion clouds surrounding the H plus and the A minus in solution. And this is in a case where we have mostly Cl minus or Na plus. So that there's that shielding effect that occurs, and that's going to be very different if you have a higher charge. That's also going to be different if you have tons and tons of these charged species and not so much other stuff. Okay, so this is just kind of an example that's not exhaustive. That's not the only way things impact, but gives you an idea of what might be happening. As you know, we say thermodynamics, and we often are saying that this is the most favorable arrangement. Of course, there's a lot of randomness there. So what's favorable is kind of what I'm pointing at, is some things will be more favorable than others. Yeah.
So does that mean that they are not going to interact with it because, like, they'll just surround it and none of the anions will interact with the cation?
No, that's not. So there will be some interaction between Cl minus and Na plus, right? There will be interactions there as well. They're no longer bound into one molecule, but the same type of thing will happen. But so that's not the point of this, because they're all in solution, so they will be interacting. But if we take a look at what's happening to the acid's activity would certainly change based on the types of things that would surround the acid groups, right? The A minus, its activity might change. The H plus might have more or less activity also.
But the salt is no longer in lattice, right? Or the lattice structure is like does not remain.
Correct. Yeah. Almost all. Well, when we describe an aqueous salt, like a soluble salt, then we tend to treat it as a forward reaction, typically, so that we don't have the backwards precipitation. Of course, we could supersaturate something and then form a solid and get that again. But in solution, we will typically describe it as fully dissociating. We'll encounter the exception when we talk about precipitations and things. But for the purpose of activity, yeah, we don't have the crystal structure or anything like that. Now, I think that some inorganic chemists working with just crystal structures and solids, you might be looking at the chemical activity of some species in that crystal structure in a solid and how it's interacting and how to deal with that. So that's a completely separate story, but the same type of principles would apply. Okay, what's the neighbors here? What could be influencing the activity of that species within its neighboring matrix? Okay. All right, so we took a look at this little figure before, and I want to explore with you the difference between taking a kinetic approach and an equilibrium approach to understanding a system in terms of the speciation. So I say speciation, what I'm saying is how much of our substance is in form number 1 versus form number 2. For example, how much of our chlorine is hypochlorous acid versus hypochlorite. So in the case, it's a simple case we use a lot in water treatment. HOCl is in equilibrium with OCl minus and H plus. So in cases like that, or in more complicated cases, maybe we have multiple acids and buffers, and we want to know how much of some mineral is dissolving. We can take a couple of approaches. And that would be assuming we've reached equilibrium, and we can use thermodynamics, or taking the kinetic approach to look at how fast the reactions are progressing forward and backwards, and find all of the different reactions and model each of them together simultaneously. That would give us a way to figure out, oh, there must be 30% in this form and 70% in that form. Both ways are possible. But depending on what you're trying to study specifically, more often than not, we will be looking at the equilibrium approach, assuming we've already gotten there, and working from there. So we can summarize it by saying either we're at steady state, meaning we've reached that equilibrium. If we look on this plot, it's kind of once those rates have equalized, I guess maybe it's more like here, right? Once these rates are here, then we've got it. Okay, so the question is, if we're doing kinetics, we're looking at the time before that. So if we're, I guess we could look at the kinetics and find this this part. And yes, I do see you if that's, if you're saying anything online, I see that. Okay. So when we're looking at the kinetic approach, mostly people will be interested in what's happening before. So all this area. What's going on, what's happening as we're reaching equilibrium? How long is that going to take? What are the dynamics? And we do have a few examples of that where that's relevant in environmental systems, such as if we have a wastewater discharge and we want to know what's happening to the oxygen downstream, and we have re-aeration happening, oxygen's coming into the stream, but we have oxygen demanding substances where the biology is pulling oxygen away and consuming it. We are in a dynamic system that's heading towards an equilibrium, hopefully back to a condition where there's a certain level of oxygen in the water. But until we get there, we might have some ups and downs based on things like the river flow, how much food for the microbes is still in there. That's a case where we are interested in the kinetic part of an equilibrium as we're heading towards equilibrium. So a lot of times we will start at, we will only care about the equilibrium. Okay, where did we reach? In cases of like simple acid-base stuff and chlorine, it happens rather quickly and we're pretty much there almost instantly. And so sometimes we care only about while we're at equilibrium. So it's kind of the two distinctions there. If we know it's going to get there quickly, then equilibrium is just fine. The book provides a nice example of some cases it doesn't get there very quickly, whereas a lot of the organic carbon that comprises our bodies is susceptible to oxidation by the oxygen in the atmosphere. It's a good thing that happens slowly so that we can sit here and not just burn up real quickly. Certain molecules would burn very quickly with this much oxygen, right? Would go through a combustion reaction. So fortunately, some reactions are slower and our bodies can account for that, protect ourselves from that, and repair that as needed. Okay. All right. So the kinetic approach finds that equilibrium by using dynamic rates and taking that approach, and we can find out how much reactant is in either in which form, or we can also just assume there's an equilibrium and go from there. So we're going to talk a little bit about each one then. So the kinetic approach tends to be pretty difficult in natural systems. So I put a little photo there. It's a natural system. You've got water very well mixed, oxygenated, and all that. You can imagine how many things are happening in that system. It's quite dynamic, from a physical point of view, but also correlating different rocks, different minerals, soil, what all is coming into the water, what all might be transforming in the water. There's a lot going on in natural systems, and it's hard to know everything. Got ahead of myself and already talked about the BOD example for wastewater. There are several examples, but we have to have systems where we know enough about the rate constants. So we need to know enough about the K for some given reaction, let's say A to B. Maybe that's K forward, and then going backward, we might have just K backwards. So we'd have to know enough about the forward, the backward, and any interactions with other species. So back to my example with the oxygen in the atmosphere, we actually know a fair bit about how oxygen interacts with water and the aeration, gas exchange, all of that. So that's good. So we have some simple things there. And if that biological oxygen demand, we have tools that are good enough to know something about it. You may have been exposed to the BOD test, and you just literally let that reaction happen a few days in a bottle, and you get some indication of that. It's kind of crude, but it gives you a pretty good indication. So that's about all you need in that circumstance to find the relevant Ks to then take the kinetic approach. But many cases, it's much more complex and maybe not so possible. Okay, so a few times when it is, here's some examples. So we've got cloud droplets containing recently emitted sulfur dioxide, and in that little tiny water droplet, which is, since it's water drop, it's like a rain droplet, it's fairly pure, has this SO2 in it, and that will oxidize to sulfuric acid. So SO2 plus O2, and in the water, you'll end up with H2SO4. So that's pretty well known, and a pretty simple system given that it's a little droplet of water. I already mentioned the BOD. Another example could be a pond that over the course of hours, you have a bunch of algae doing photosynthesis. They're producing a lot of oxygen. Then at night, you'll have the reverse, so during the day, you'll be taking CO2 and producing oxygen. During that time, the pH could rise because you're removing CO2 from the water, and you're sort of removing a bit of acidity. The reverse will happen at night, and the algae will then, and all the bacteria will be doing respiration instead, and you'll have some oxygen depletion that way. Okay, groundwater seeping into the surface, bringing Fe2+. Once that's exposed to air, that tends to oxidize to go Fe3+. And we generally have a pretty good understanding of those particular rates. And eventually the iron then will precipitate as iron hydroxides, so FeOH3. Okay, and that'll give you that slimy orange looking stuff. Sometimes that's bacteria aiding that process. And if you've ever wandered in like a creek or something, a river, and you're like, ooh, what is that orange mess? Is this some nasty contamination? Looks awful. It's probably just some iron and iron reducing bacteria sending the iron out, and then it's rusting. So it's actually pretty natural, all things considered. Okay, last example here, we have contaminated groundwater flowing through an engineered subsurface trench. It's filled with Fe zero valent iron, so like iron, metallic iron chips and filings. Doing that so that they can give those electrons and transform trichloroethylene, TCE, to perchloroethylene, ethylene, PCE. So that would be a way to transform a contaminated groundwater, making it less hazardous, maybe easier to remove, and that's pretty well known. So just tracking that particular reaction. So there are some cases where we have these reactions that we know enough about the kinetics to accomplish what we're trying to do. Okay. Now, the book also provides another example, and this one's more of the math behind how you get there. So we're going to take a kind of big picture look at this. We don't need to learn so many of the specifics. In this particular example, I just want to show you kind of how it would build into taking a kinetic approach to understanding the ratios, like the speciation. Okay, so in this case, the author says we have a metal, that would be the M, reacting with some ligand, L. Now ligands we will cover in more depth, but they are molecules that can interact and bind with metals and form a complex. So M and L, the two species, and we have two reactions. One is a forward reaction for them complexing, forming together the ML, and the backwards reaction, that splitting back apart. So it's not like it's a really, really, really strong reaction that just sticks there, a forward reaction. It's reversible. So sometimes the metal and the ligand will separate again. Okay, so if we were to try to describe and look for a way to ultimately compare the amount of ML, maybe in a ratio versus M, or maybe we just want both of those quantities, how do we get there based on the rates? That's what this is showing. So we could look at the rate of change for dm dt, so the rate of change of M, that's going to be equal to producing it through the backwards reaction. That's this here. That's that term. Subtracting it from the forward reaction, that would be this term. That would be our mass balance, right? That's the source of it and the destruction of it. So we're doing a mass balance on M for that. We could solve that. And separately, we can also describe the total amount of the metal here. M total would be what we started with plus the ML that we started with. And at any given time, that's still just the current amount of M plus the current amount of ML. That's just saying is we're not creating or destroying M, so the molar amount is going to be the molar amount of anywhere that species shows up. We can do the same exact mass balance and the same exact total balance on L. So we have two balances. One is just the total balance, and one is this mass balance of over time. Okay, so we can then do some substitutions and substitute, instead of L, we can substitute the total minus the ML. That's just going to give us a way to solve and put things in, and we can rearrange the change in M over time accordingly because we have too many unknowns in this equation, right? So then we can do that substitution and get pretty much everything in terms of M instead. So that's just what the book's doing here. That'll get us to a point where we can describe these with the rate constants and then continue to solve. So well, in this step, I missed a part. We assume we reach equilibrium. And at equilibrium, we no longer have a change, right? So at this point, this is saying we've reached equilibrium, which is nice because it doesn't actually matter how long we have. We can just say, well, eventually we'll get there, right? That's the assumption. Once we get there, here's going to be the condition, and that's this kinetic approach. Okay, so then at that equilibrium, then we can have 0 on the one side, and we solve that equation. Again, I'm not wanting us to go too far into it. I just want to see what this would look like process-wise. So then we have the balance of the backwards reaction on the left and the forward reaction on the right. And you can see that here with the B and the F. Okay, so then we can say all of these then are essentially the equilibrium values. So MLE equivalent or equilibrium, we're just going to note it that way. So then we can simplify all of this and say at equilibrium, here's the deal. And we can then get that ratio. Turns out the ratio of the rate constants is essentially the ratio of the ML divided by the M times the L there. And that gives us our equilibrium constant. So based on that kinetic mass balance approach, we can find the ratio that describes equilibrium. And that's true for any type of kinetic system where we can arrive at an equilibrium. Now this is a rather simple one. We have one forward reaction, one backward reaction, but we had two mass balances to solve in the sense of the mass balance on M and L, or at least we had to figure out what to do on that. You can imagine if we have a second equilibrium in the system, things will get more complicated very quickly, right? So sometimes we can take this kinetic approach, and if we can find out the rate of the forward reaction and the rate of the backwards reaction, we can pretty well describe the K. Not always that simple. Okay, so sometimes it will never work. And we have an example here where we have, let's say, reactants A and B, and it looks like maybe we will have an equilibrium where we have A and B dissociates to A and B, and then A and B can recombine to AB, but we also have A going to C. And that's a forward reaction and never coming backwards, and C is not participating in any other way. Well, that just kills it, right? That just means no equilibrium, because eventually we just run out of A, and if we let this go for a long time, we can actually see that we will end up with some B and C. There should no longer be any AB or any A if we just let that go forever, because A is simply being consumed by this third reaction. Perhaps if it's really, really, really slow, then we'll have an equilibrium, effective equilibrium for some time between these two if they're much faster. But over a long period of time, this would really matter. And if it's fast, then over a short period of time, we just will never get that equilibrium. Okay. Now, if we did have something like C plus B in a different reaction reforming AB, then perhaps we could come back to an equilibrium. But again, complicating things, right? So yeah, that's kind of the gist and the limitations for the kinetic approach. Does that make some sense? Kinetics being the let's see how fast this is going, let's find the actual rate constant and put that into our mass balance to figure out where the mass is finding itself, right? Okay, so good. Now, the alternate would be the equilibrium approach, and technically this is thermodynamic equilibrium, but that's just what we're always going to, anytime we're talking about equilibrium, it's going to be in the context of thermodynamics, so we're just going to call it the equilibrium approach. Now, this is possible when we have a constant temperature and pressure, or when we have a constant temperature and volume. And the authors of this book are very happy that we don't have to deal with volume too much. I guess it's not an atmospheric type chemist. In aquatic chemistry, we are almost always having constant pressure. I guess occasionally if we were to do something at the ocean floor, we have some differences in pressure there compared to at the surface, but even there it would be pretty constant within that system. So In the case of gas phase systems, we can still do thermodynamics. It just takes a little more calculations up front. And as it describes here, most systems are the easy way for us, because the K values, the equilibrium constant values, for the condition where pressure can change and we're keeping the volume constant, we actually have to solve that first. So it gives an example. If we react 1 mole of hydrogen, H2, with half a mole of O2, we're going to get 1 mole of water. If we do that and we do it in a piston chamber that equalizes the pressure with 1 atm, we all know, we know the K values since we know the final temperature and pressure. But if we do that in a system where the final equilibrium pressure value depends on the final equilibrium chemical distribution, then we have some trouble, if I said that right. Okay, so I think it elaborates a little further on that, but basically it's going to say, okay, well, now we have to calculate how much, what is the volume of this condition if we did this. So the oxygen and the hydrogen, these are gases, so we're going from a gas to a liquid. So that system can get more complicated. So if you wanted to read a little more about it, you've got the heading here and you can find that pretty easily. So all that to say, we just need a constant or a pretty standard state system. It doesn't have to be the standard state, but we have to have a state that we can describe and account for. Okay, so this is where this formula that I already introduced to you comes from, and we can be a little more exact here and introduce the activity coefficients. So we briefly talked about it, but the K equilibrium constant, the uppercase K, is I've been calling this, and I haven't been very clear, but the uppercase K with some subscript is an equilibrium constant for K, or for X in this case. So maybe we put W there, it's for water. Maybe we put Ka for one reaction, reaction A or something. Or maybe we just write Keq for the equilibrium constant. People write it in different ways, but the K there, the uppercase K, that's an equilibrium constant. In a general way to describe it, for a given reaction here with A molecules of A reacting with B, yielding C and D, this is the way to describe it, and we ought to do it with the activity coefficients here. So we can say the activity of C raised to this lowercase c power times the activity of D raised to the D power divided by the reactants in the same manner. Okay, in dilute systems, we can just pretty much do moles per liter, like that. So that's kind of where we come up with that system. A lot of times it's nice and simple, and we don't even have stoichiometric coefficients out front, and so it just becomes quite simple. Like in the case of water, the Kw is just simply, it's dilute enough that we're not even doing the activity. We have no exponents. Just looks like that, right? So that's the deal, and that's, by definition, that's how we describe K. Now, in order to use these, we do need good information on the equilibrium constants. So if we want to know, we showed that we can potentially derive the equilibrium constants from kinetics, or maybe we can do these types of studies and derive it and identify typical equilibrium constants for a given species or combination simply by studying a system, right? So we need good information on those equilibrium constants to apply these in general. And that means if we get a database of them, that's really useful. So then we can combine multiple equilibrium models together or equations to model a wider system. That would be kind of the deal. So the first kind of computer model, all the way back in 1976, that was read EQL. Since then, the Mintech system has been published. That was EPA in 2006. And at least when the book was published, that's still out there. So that's something we will also take a look at and explore. It might be a computer application that we can download and then run a system. Maybe it's a web portal, I'm not sure. Okay, sometimes we have slow reactions and we can just kind of ignore them. So an example for that, and again, this kind of relates to the kinetics, but in terms of dealing with them from an equilibrium perspective, we know that it's not technically at equilibrium, but we're going to treat it as if it is because we need to know what happens now, and we don't care that some other reaction is going to happen in the course of a week. Right? The relevant chemistry might be what happens in the next hour, and if it's approximately at equilibrium over that hour, great. Our chemical reaction, our engineered system doesn't care, perhaps. Okay, so an example would be increasing the pH of a solution containing a lot of dissolved Fe3+. It will initially yield FeOH3 solids, iron hydroxides. But in time, that's going to change into the mineral geothite, kind of a different iron hydroxy mineral, which is more stable, less soluble, so it's more likely to be coming out of solution. But that takes a bit of time, and so we can occasionally just ignore that. And so in that example, the book goes on to use that as an example to say, can be assumed with good results for relatively short times, days to weeks, that the FeOH3 solid, rather than that other one, governs the dissolved concentration of Fe3+. So the FeOH3, those reactions are kind of a bit quicker, even if they're not immediate, and the transformation from that to the geothite takes a lot longer, and so we kind of just ignore the geothite for a lot of cases. Okay, so that's all I had for you today, and we will pick up there and go on further, probably starting on some problems with that next time.